On the 28th of August, the moon will slide almost entirely into the shadow of the Earth. Not a sliver of it, not a bite taken out of one edge. About 93% of the lunar disk will sit inside the darkest part of our planet's shadow. And yet it will not disappear. To understand why, you have to understand what a shadow actually is when the object casting it is a planet with an atmosphere. Earth's shadow is not a single dark cone. It has two distinct parts, and the difference between them decides everything you will see that night. The outer region is called the penumbra. Standing there, you would see the sun partly blocked by Earth, but still shining. The moon passing through it dims so gently that most people never notice. Photographs barely register it. This is why penumbral eclipses are technically events and practically non-events. The inner region is the umbra. Here, Earth blocks the sun completely. No direct sunlight arrives at all. By every simple rule of optics, an object inside the umbra should be invisible, a black disk against a black sky. That is not what happens, and the reason is standing right above your head. Earth's atmosphere wraps the whole planet in a shell of air roughly 100 kilometers deep. Light passing through the edge of that shell does not travel straight. It bends inward, refracted, the same way light bends through a lens or through a glass of water. Some of it is steered into the shadow. But not all colors survive the trip. Air scatters short wavelengths far more efficiently than long ones. Blue light is knocked sideways, spread across the sky, which is precisely why the sky above you is blue at midday. Red light passes through with much less interference. Now stretch that same effect to its limit. At sunrise and sunset, light travels through far more air to reach you, so the blue is almost entirely stripped away, and what remains is orange and red. Every sunset you have ever watched is that filter at work. So here's what actually reaches the eclipsed moon. Sunlight that has grazed the edge of Earth, been bent inward, and had its blue stripped out. It is, quite literally, the combined glow of every sunrise and every sunset happening on our planet at that exact moment, projected onto another world. That is why the eclipsed moon glows red rather than vanishing. The shade is not fixed. It shifts from bright orange to deep brick to an almost brownish gray, and it changes from eclipse to eclipse depending on what is floating in our atmosphere at the time. After major volcanic eruptions, when the upper atmosphere is loaded with fine ash and sulfate particles, eclipses have appeared unusually dark. Observers have recorded eclipses so deep the moon nearly disappeared. Dust storms, wildfire smoke, and cloud belts along the shadow's edge all leave their fingerprint on the color. Which raises an obvious question. If the moon orbits Earth roughly every 29.5 days, and the geometry lines up every single month, why is there not an eclipse every month? The answer is a small tilt with enormous consequences. The moon's orbit is tilted by about 5 degrees relative to Earth's path around the sunday. Most months, the moon passes above or below the shadow entirely, missing it. Only when a full moon happens near one of the 2 points where the orbits intersect can it enter the shadow at all. Those crossing points are called nodes, and they drift slowly over time. This produces the rhythm astronomers have tracked for thousands of years, eclipses arriving in seasons, clustered, then absent for months. Ancient observers noticed that rhythm long before anyone could explain it. Babylonian records cataloged eclipse cycles with enough precision to predict them. That predictive power mattered. An eclipse was one of the very few celestial events that could be forecast, and forecasting the sky was, for a long stretch of history, indistinguishable from holding power. Watching one is remarkably simple. A lunar eclipse is entirely safe to observe with unprotected eyes, unlike a solar eclipse, where looking directly at the sun causes permanent damage. There is no filter to buy and no equipment required. You only need a view of the moon and a little patience. Give your eyes 15 to 20 minutes to adapt to the dark and avoid looking at bright screens during that time. The color becomes noticeably richer once your vision adjusts. Binoculars will not reveal more of the eclipse itself, but they will deepen and saturate that copper tone considerably. For this eclipse, observers across Europe, Africa, and the Americas are positioned to see at least part of it. The exact timing depends on where you stand, so check a local source for your city, but the event itself unfolds over hours, not seconds. There is no single moment you can miss. And this is the part worth holding on to. When you look at that copper disk, you are not just watching a rock pass through a shadow. You are seeing our own atmosphere, its dust, its weather, its chemistry written in light across the surface of another world, 400,000 kilometers away.